Welcome to another Teardown. This time we're taking a look at the CurrentBody LED red light therapy mask. Keep watching to see me try it out, take it apart, and analyze the design and manufacturing of the circuitry inside. I'm Becky and I love to make things, but I also like to take things apart because it's fun to learn how things are made. My friend Michelle from Lab Muffin Beauty Science sent me this mask. It's basically a flat, flexible LED panel meant to be worn on your face. It's got a long USB cable that connects to the battery pack. See, Michelle, my other friend Ruth Amos, and I are all very curious about these devices. How do they work? And what's the science backing up the marketing claims? Is it really worth the $400 price tag? Could we make a DIY version? We all got on the horn to talk about it.
I honestly think with most skincare things, it is how motivated you are. Like, cost benefit is so subjective. But for this, I think it is actually pretty cool what it does. There is quite a lot of, there is pretty solid, moderately solid, biological, like proper peer-reviewed evidence. And there's also really good reviews. So with the combination of both, I feel like it's one of the better options if you can handle having that on your face or lying under the really bright thing at the dermatologist.
Recently on TikTok, there have been lots of things around red light replacing people needing, like, having Botox, like for certain things or certain skin issues, having investing in LED red light rather than having Botox. Is that just two things that people have decided would make good TikToks, or is there like actual evidence on that? Does that make sense?
I think for Botox specifically, it doesn't really do what Botox does, but I think this is probably more similar to things like retinol, for example, something that goes in and increases collagen. So this can increase collagen and elastin. It can also speed up healing and reduce inflammation, which are also things that retinol tends to do, retinol, tretinoin, all of those. So I think in terms of skincare, it does a lot of anti-aging things. And I think one of the big benefits is that it doesn't seem to work in the same way. And a lot of the time, if you're trying to target a particular concern like wrinkles, you kind of want to use multiple things that work in different ways, and that should, in theory, work better. So I think that's really a lot of the attraction. There's also a whole bunch of things about, like, just because it seems to be such a general sort of treatment, it seems to work on like all sorts of cells. There's all these studies on things like muscle repair and things like that. So yeah, I think a lot of that kind of thing is where the attraction is, with things like regrowing hair as well. There's like helmets that have red lights inside them. There are these giant red panels that a lot of those biohacking podcast bros tend to use. It's definitely oversold in a lot of circles, but I think it is possibly one of the more well-supported, expensive home things you can invest in.
So essentially, when making something that's good for the skin, it's about the wavelength that it gives off. So you're looking at the 630 plus?
Somewhere around 630, probably plus or minus 10 is probably good. And then somewhere around 830, again, probably like there's some wiggle room, probably another like plus or minus 10.
I guess one way to be able to tell if your mask is got near infrared is to actually look at the LED very, very closely. And if you only see one black dot, it's only one wavelength. And if you see two black dots, it's two different LEDs and they can be two different wavelengths. Be sure to check out Michelle's video for the science of how red light therapy masks work, and Ruth's video where she DIYs her own. This is a collab across 3 continents. We figured it would be useful to be able to evaluate and test the products and components to compare notes, but turns out spectrometers are expensive. So I set about building a simple Arduino circuit that spits out the values from a light sensor to the serial monitor. It's not super precise, like the buckets of wavelengths are big, so I don't really know if Michelle will find it useful for science purposes, but it's worth a try. I could tell the difference between the readings of the mask LEDs and a plain red LED, for instance, verifying the presence of some near IR. I used Tinkercad to make this part that holds the light sensor circuit, and 3D printed it on my Bamboo printer. You can find the file, the circuit diagram, and code at the link in the description. The sensors and microcontrollers were provided by DigiKey, the sponsor of this video. They carry DIY boards and components for all skill levels, as well as tools for putting things together and tearing things apart. If you're coming here from Michelle's channel and are therefore into beauty, DigiKey's like the Sephora of electronics components. To access the bare electronics inside the mask, I cut open the clear plastic cover. Inside, there was another white plastic piece that covered up the circuit board. Freed from its silicone cage, it's now time for my channel's favorite electrical engineer, David Craner, to join us to take a look at the circuitry inside. Oh, hey, David.
Hey, Becky.
Come on
How's it
in.
going? Oh, nice new plant.
Somehow your microscope beat you here.
I couldn't imagine how that happened. How's it going? What do we got?
We have this LED face mask.
It's definitely a look. An aesthetic. I feel like King Leonidas or something.
Do you want to try it with the LEDs actually on?
So what is this doing to my skin right now?
It's purportedly causing your skin to regenerate its cells faster.
With LEDs. That's
Yeah,
cool.
so, giving you a youthful glow.
I've always felt like being around lots of LEDs is good for my health, so wait, what if I do it like this? Can I get my glasses on top of it?
Could you wear it for 30 minutes a day?
Probably. I could go to the bodega. Does it have a belt clip on the battery pack?
No, you put it in your pocket. Come on. Your
that's true.
clothes have so many pockets.
That's true.
Does it have a belt
clothes
clip?
with pockets. Yeah, exactly.
So my friend Michelle sent this to me, but the thing is like exorbitantly expensive. So
how much does it cost?
hundreds of dollars.
Wow.
For this one piece of flex PCB and this like silicone
Situation.
enclosure, if you will.
Yeah. Okay.
So that's the thing that straps to your face. I can't stand the feeling of this plastic. I know it's like a little dirty right now, but
squicky. Well, let's take it apart and make a better one.
yeah. So I've already taken it out of its enclosure.
Okay.
And it is indeed just this big piece of flex PCB.
Uh-huh.
I thought we could look at the LEDs themselves under the microscope.
Okay. Well, these are like 50-50 lead frames, right?
That is the size of this LED, yes.
So that means that's like 5 millimeters by 5 millimeters, right?
Here we go.
Number 7.
This one's number 7, yeah. I didn't count them manually, but there's a label that says 49, so that's how I know there's 49.
I mean, I know we've looked at multicolor LEDs before, and it's pretty cool. I mean, I think it's pretty cool that this lead frame is like pretty much the same as other 50-50 form factor LEDs we've looked at, like the smart LEDs.
RGB,
Yeah, the RGB smart LEDs. But it's cool. It's interesting because you see it's like the same plastic around the outside, but it doesn't have the little computer chip inside that makes it smart, and it only has 2 dies.
Yeah, it's leaving that, like, those 2 shiny pads on the left side aren't being used.
Yeah, so it's an interesting illustration of how like different things in the supply chain come together to make different products, because it's like the same package on the outside, but you can see the actual LEDs, there's only 2. So far, that lines up with your guess that this has a red and an infrared inside of each one. But I know that you measured them using
my little DIY spectrometer thing, yeah.
But I mean, to me, this looks like LED. It's not
as advertised.
Yeah, it's not a smart LED because you can see it's got these. Each one has 2 little resistors next to it, so I'm guessing that those are like current limiting resistors. And then you got 2 LEDs inside of each little.
You can see the die
box.
is that tiny little square brown part, and then each one has a little wire flying over to the other shiny.
Yeah. It always just blows my mind how this tiny little square is like the thing that makes the light. Like so much light comes from. Yeah, look. Oh yeah, you can see that's probably infrared and that's probably more red.
Yeah, it's still operational.
But it's crazy that just like so much light comes out of a small. How big would you say those things are? Like less than a millimeter square? Like
for the uninitiated in the audience, like. Why is it cheaper to use this like pre-existing? Like, why is it this shape and not a shape with just 2 sets of shiny bits?
Yeah, well, it's because this type of package is made like a lot, and so when you're making stuff, it's
like all digital signage, like LED advertisements, all of that stuff is using like this
plastic,
this same plastic shape. So they're made by the billions already for the advertising and whatever other
for the everything that has
screens,
multicolor LEDs in it industry.
But which is in the world a lot of this is what screens are made of. Big screens, not
There's
like
some big screens, some billboards, like your old friend the WS2812 uses the same lead frame, I'm pretty sure.
Yeah, I think so too.
I think. And so so if you want to have like a custom LED, it makes more sense to like take a lead frame that someone's already designed and then put your own stuff.
Because all of the equipment is already set up for.
Because I mean, this is like this lead frame. It's not a super simple part, right? It's like this like little tiny plastic injection molding, and then it has some metal work for the legs, and it has the stuff inside that the wire bond gets to. Like this lead frame, it's not super complicated, but it's not a trivial thing. So if you can just take advantage of someone else already making that and then putting whatever colors of actual light emitting diode dyes inside that you want, then that makes a lot more sense.
How can we tell?
And then also when you put them in here, since you're combining the red and the infrared into one little box, you don't have to assemble twice as many things when you're like placing them on the PCB. Instead of having a bunch of red LEDs and a bunch of infrared ones right next to each other, it makes more sense just to put them all inside the same little package.
Cool. How can we tell which one is infrared and which one is red?
This one that we think is the red one is much brighter than the one down here.
Yeah.
That you can see it's glowing, but you can't see it that much. So I would guess that that's closer to the infrared one.
Given what I know about camera technology, that has to be it, because this is like the simplest or like oldest style camera sensor in the room. And
I mean, if you really wanted to get exacting about it, you could like take off one of these resistors to turn off one of the LEDs inside, and then clock it with your
my measuring device. Yeah. Ooh. And then I guess that brings me to the next question. Like, are they wired in parallel with each other? If I were to disable that one, would it disable just the red LED on that one, or would it disable all of them? Because we haven't looked at the traces to see.
Yeah, I don't know. I haven't really looked at the traces.
We would be able to tell by looking at the scan more easily, right?
Probably.
Is there anything else about the physical device? Did you want to shout out this thing?
I just like this. I like the strain relief that they did here.
With a hole instead of like a through hole, plated through hole in the flex, which is hard to do, right?
Which is irritating. I mean, you can, but it just kind of sucks as a thing. So it's
a surface mount pad and a hole.
And it goes through. If you yank on the wire, like the strain is much reduced by this, and so because PCBs, if they take a lot of like load, you can just pull the pad straight off.
Shear it off,
and then you cry, yeah.
Yeah, and you cry because it's broken forever and you can't fix it.
Can't fix it. Oh yeah, you were talking about these lumpies on the back.
Oh yeah.
My guess is that those are just like more metal to do heat seeking. Since like, how long do you leave this on your face at a time?
15, 20 minutes.
Yeah, so it's like like in an LED strip or something like that. The LEDs are usually like twinkling on and off, and they're not at full brightness.
Right.
Like these are just all the LEDs on full brightness all the time. So I bet that like heat dissipation was probably a
concern.
That is wild. Yeah. I think heat dissipation is a thing that you probably want to be thinking about. I mean, they don't feel like they're getting that hot, but then maybe the heat sinks.
Heat sinks are effective. Yeah. I think the motivation for me wanting to make one myself is like, well, first of all, as a group, me and Ruth and Michelle want to answer the question, like, is it really worth it to buy this commercial device? If you have any engineering savvy like I do, can you actually make a device that's comparable for cheaper or a better device for the same price?
Yeah.
And I don't like wearing this. No. Like, I would love to have skin like Ruth, who puts a lot of effort into her skincare, but I can't stand the feeling of this touching my face. So I feel like my motivation to want to make one myself is like, well, I can, and that's fun. Yeah. But also, I would make it a little different. Maybe I'd put it in a baseball hat. And like make tunnels for my eyes so that I could actually see you while this is going on.
The speculars on your eyes look really cool with all the reflect. It's like a ring light, but like scary looking.
With a Halloween costume, right? But I could put it in like a baseball cap, and then if I made tunnels around the eyes, then I could actually sit and use my computer while I'm using this. Whereas
you could probably do that.
compliance makes the difference for this. If you use it every single day, you get the results. If you don't, you don't. So for me,
when you say compliance, you mean like you're doing what you're supposed to be doing, not material compliance. You're talking about like
correct
patient compliance.
Compliance, like clinical adhering to the plan, using it every day for the amount of time that you need to use it to meet the efficacy rates from the studies that they did that prove that it works. Or whatever.
Let's look at the scans.
Okay.
Thanks to our friends.
Our friends at Lumafield, who have scanned yet another thing for us graciously. And I would like to say they don't just scan; they also like process the scans into nice, readable bookmarks for us, so that we don't have to do.
Dig through it.
They wrapped it around itself or some floral foam, and then that's why it's curved in here, which is cool to show the flex. So you can see the traces. And I'm curious to use this scan to reverse engineer and try to make my own one of these PCBs. Maybe not even to get it manufactured, but just to price it out to see how much it would cost to get it manufactured. So what do you notice about the wiring inside? Or like, can we see those metal bits that you were talking about?
Can you see the metal bits?
Or maybe they're just stiffeners.
Not too much, huh?
Are they just stiffeners instead of heat sinks, maybe?
I don't know. I mean, in my experience, stiffeners are usually applied to like the outside of the stack, but that's just, I'm not a super duper expert in flex, so they
But
could
if
be
it was
in the
metal,
middle.
wouldn't it show up here?
I would think so. So they could be. But why are they different? They're like different lengths.
Yeah, because sometimes they go over an LED and its neighboring resistors.
Maybe it could be that.
If it's not showing up here as bright white, which would be metal, I think it's not metal.
It could just be there for that.
And then it's just a stiffener. So what layer on the Gerber file describes the stiffener?
Whatever one you want, as long as you tell the house which one that it is.
Okay.
So if you look at where like the power is coming in, which one of those is plus and which one is minus?
The one on the outside, so on your left on the screen, is ground. Or is ground going to be like just everywhere but the power? Like, is this all a big ground plane?
Where do the grounds of the actual LEDs go? That's a question.
Well, what I think is that this is all one plane. I think there's a ground plane, and this is metal. And the only part that's not metal is this little black strip around this trace.
That's the clearing.
And I think that this trace is on the other side of the board. I think it's like two LEDs in series, then a bunch of pairs of two wired in parallel. Yeah.
Yeah. So there's like a lot of sets.
This one and this one, this one and this one, and they like share resistors and a power and a ground.
Yep.
Like this one and this one. This one and this one.
Yep.
And so that makes sense if they're getting power from USB, which is 5 volts. Each of the LEDs is like a 2.4 volt LED or so, right? That's
1 to 2 and change.
1 to 2 and change is normal for a red LED. So you can put, depending on what resistor you use, you can put 2 in series and then a smaller resistor and get up to that 5 volts.
Exactly, because you're just setting the current through the whole stack. So if you just put them in series but don't exceed the total voltage drop of your power supply, then you set the current limiting resistor so it gives you the right amount of current.
Right, so 2 LEDs is like the max for a 5 volt circuit, so it's just doing pairs and pairs of 5 volts across the whole thing. If you didn't do them in pairs like this and you did just a power and ground to each LED and a set of resistors, you would need more resistors and you would need higher resistance resistors also.
Yeah, which means that you'd be...
And you'd need twice as many resistors.
Which means that does mean that you'd be using more power, right? Because more power would be dissipated.
They'd be wasted as heat. Yeah. So this is an efficient thing both in number of components and energy consumption.
Yeah.
So I will try to knock it off as precisely as I can in the software. This looks like a fun routing job. How much, in your estimation, would it cost to make this product?
The whole thing together.
Sure. The PCB, battery pack, silicone, whatever you want to call this, the enclosure.
Well, first I would figure out how much are these LEDs. We tried to find...
We looked at some standard 50/50 RGB LEDs, and they were as cheap as like 17 cents, or like between 17 and 30 cents.
17 cents, and that's only for 1,000. So this product is probably made in like the tens of thousands.
Sure.
So if we're conservative, call it 17 cents an LED, just to be conservative. And there's like 40.
There's like 49. Call it 50.
50.
Call it 50.
50 times 0.17. Remember, that's $8.50.
Okay, so the LEDs on this product.
So call it $10 of LEDs, and then I would guess a flex PCB like this in those kinds of quantities is like a couple bucks. Call it $5, although it probably costs less. But
when I spec'd it out just this size and shape from like one that I can buy, which is, you know, with like markup and all of that stuff, it was $54.
In quantity, like
5.
Okay.
Yeah.
So
the setup cost is and the, I guess the edge punching, like they don't route it, they laser cut it.
yeah. So if you do, so that's one thing about flex PCBs is if you are doing a low quantity, they'll laser cut it, which charges you more because it's more work intensive and runs the machine. But if you're making a lot, you can like
they'll make a die.
Yeah, you can like do die cutting by other means. So,
Yeah.
So like I would guess I'm thinking in terms of like at quantity 10,000s level.
It's like, so say $5.
I would call it $5 for that.
$10
$10
for the LEDs.
for the LEDs.
But then also the assembly and stuff, the setup charge, you have to make the die, you have to load the feeders for the parts and all that stuff.
Yeah.
So like there's labor involved.
It all comes out. I mean, this is probably a couple dollars, depending on how they cast it. I mean,
So let's call it 5.
Yeah, basically this thing
$5
costs less. It's less than $50. It's probably less than $50. It's probably
Okay.
between it's probably between $25 and $50. That's just like a super rough, like conservative guess.
And then they have nice packaging, but we know that beauty products have the highest margins out of like any consumer goods, higher than electronics, higher than anything. The margins are insane. And that's part of why the packaging is insane, because there's so much extra money and also so much more ephemera to try to get you the product, which the product itself is not not the thing you buy. Like you buy into the marketing. Like there's so much room. There's so much.
The battery pack thing's probably a couple bucks, but still, I mean, if this thing costs $450, there's at least a 10x markup. Is the point?
Yeah, and that's kind of normal for beauty products to have such a high margin. So, and also because in the beauty space you're dealing with a luxury buyer, just like early wearables all were for skiers, because like what market is gonna tolerate an expensive first to market product? People who are already spending a lot of money on something recreational. And I'm not calling skincare, like everybody has skin and that needs care, but like this level of skincare is like a recreational activity.
It's recreational.
That therefore people aren't. It's not a necessity. People are willing to spend money on it as a splurge. So the amount of splurge is pretty flexible. And the manufacturers of a product like this know that.
If you being a person who knows how to make things, it would be really funny if you could just like make this yourself for way less.
Well, I think I could make one that since I don't like wearing this one, I think I could make one that I do like wearing, which would mean that I would get the benefit of the science at all. Where I'm not going to get the benefit of the science from this one because I'm not going to wear it.
Right, exactly.
So for me, the definition of success would be something I'd actually wear that costs the same amount of money or less than the one that you could buy.
Right.
Cool. Well, thanks, David.
Yeah, no problem.
See you next time.
Should I go back out?
You can use the stairs.
Oh, okay. All right. Well, see you later. Bye, Andy Rooney.
To me, the logical next step was to try to replicate this product's circuit board in my PCB design software and get a quote from a manufacturer to find out the price. I scanned the mask and traced the outline in Illustrator and saved the drawing as an SVG. In Fusion, I was able to import the SVG as a board outline. You've seen me do this before in my PlayStation 4 controller breakout board project. Then I drew out a simple circuit where every LED is wired in parallel and has its own resistor. I started to lay the LEDs out on the mask, but took a break to figure out the exact footprint I'd be using. It was time to source the bicolor LEDs. At the time of this video, JLC only has 2 products that are even close. Both have one red and one infrared LED, and they are about the right wavelengths. Good enough for a quote, at least. The other option would be to use separate red and infrared LEDs. I positioned the LEDs where they are on the commercial mask, then added a few extra, to be honest. I routed the board and added a layer that specified where the stiffeners should be. Basically, behind every area there are components. Then I exported the Gerber file, which contains the board specifications, and created a bill of materials, or BOM, and component placement list, or CPL. These 2 files specify which components to use and how to orient them on the board. Along with the settings for board thickness, etc., this is all you need to see how much it would cost to get these made. JLC PCB has a minimum order quantity of 5 pieces, and the total price quote, including shipping, was just under $300 US. So if you and 4 friends go in together, they'd each be $60. That's before the battery and strap situation, but still a lot cheaper than the retail price. I just missed the deadline to get these made with JLC before the Chinese New Year holiday break, but honestly, just quoting it out was really useful in understanding what goes into this product. Let me know what I should tear down next in the comments. And be sure to check out Ruth and Michelle's light mask videos too. If you liked this video, please give it a thumbs up and share it with a friend. I hope you'll subscribe with the bell to be notified of my future uploads, subscribe to my email newsletter, and find me on your favorite social media platform. Thanks so much for watching, and I'll see you next time. This video was made with support from my sponsors and generous donations from viewers like you through Patreon and YouTube memberships.